Okay, so in the last screencast, I talked about what energy is and how it's measured. And this one, I want to talk about how we generate it in our society. Because it turns out that electricity is just this very usable form of energy. It's a great way of distributing energy out to all the users in a society. And so it's definitely worth our time to just learn a little bit about how exactly this process happens. Okay, so the reason electricity is so useful is that it's a form of energy that's most easily converted to other forms. So you can take electricity, which is, remember, that's just the kinetic energy of electrons and wires, and you can convert that into sound, like for speakers. You can convert it into light energy quite easily. You can convert it into heat energy. You can convert it into the motion of your car. It's just easy to convert it to lots of other forms, and for that reason, it's something that is the preferred form of energy to use. Now, it's very difficult to go the opposite way. It's hard to turn other forms of energy into electrical energy, but it's easy to turn electricity into other forms. And so societies have just decided the best way to distribute energy is through what we call an electrical grid, a bunch of wires in which we are putting energy into the electrons and letting the consumers access that energy. Now, let's remember from the previous screencast, the first law of thermodynamics tells us you can't create or destroy energy. The power company's not making energy. Nobody makes energy. It can't be made. All right. The first law says that you can take energy from one place and put it somewhere else, or turn it into another form, but it has to come from somewhere. It has to go to somewhere, and the total amount never changes. So, in order to generate electricity, generally speaking, we look for sources of potential energy. Newer approaches involve directly capturing one form of energy, a non-potential energy, like say wind energy or light energy, but that's really a small amount of our energy production right now in our society. The vast majority of the energy that is used in our society comes from potential energy sources. The main one is fossil fuels. So basically, these plants captured sunlight years ago, and they've been converted into coal, oil, and natural gas. We'll explain that in this unit. So we have all this chemical potential energy stored in the bonds between carbon, hydrogen. Now, we have uranium. So uranium is basically nuclear potential energy. It's energy stored in the between the protons and neutrons in uranium atoms or plutonium atoms. And then we could have water behind a dam, hydroelectric power. So basically, we have high water in a high energy position, and as it flows to a low energy position, we are able to convert some of the energy into electrical energy. So let's just talk about how it happens. So regardless of whether I'm using uh, coal, natural gas, nuclear, or hydroelectric, in every case, essentially what I'm doing is I'm spinning a propeller-like device called a turbine. And this turbine is basically a series of propellers that are connected to an axle. And when this turbine, sometimes I'm going to say turbine, sometimes I'm going to say turbine. I don't know why. I've always mixed the two up. But basically, what happens is when this is forced to spin by either the flow of steam, the flow of air in the case of a windmill, or moving water in the case of a hydroelectric power. Basically, these propeller-like devices called a turbine is being moved by the flow of a fluid, and then it's connected by an axle to this thing called a generator, which houses a bunch of coils of wires that are forced to spin inside a very powerful magnetic field. And it turns out that when you spin electrons inside a magnetic field, it energizes the electrons and converts this kinetic energy of the spinning turbine into the electrical energy of the kinetic energy of the electrons in a wire. So here's a good illustration of how that works. So basically, here's my magnetic field. This would essentially be a stylized turbine. So the idea is I'm moving a coil of wires, and as I move that coil of wires, it forces electrons to go back and forth in these wires. And in doing so, I can then take that energy that was kinetic energy here. It's now electrical energy here, and now I can convert it into light, music, whatever I want to, because electricity is so easily interconvertible, easily converted. Okay. Now, where do we get most of our energy in society? Well, look at this graph. Now, this is from 2010, and things have changed a bit. Okay, it was 10 years ago, but look at this. It hasn't changed that much, just so you know. So, and this is just the U.S. It's a little bit different for the world, but it's very indicative of what we find. Almost half of the electricity generated is generated by burning coal, and then about a quarter of it is by burning natural gas. both of which are fossil fuels that produce carbon dioxide. Now, about a fifth of it is produced from uranium, so from nuclear power. And then about 6% of it, like less than a tenth of it, is coming from hydroelectric dams. And this tiny little slice of it, which is growing, and that's good, is coming from other sources like wind and solar. But obviously, if you look at it, like 3/4 of the pie is essentially fossil fuels. That's a problem, and it's changing, but it's not changing as fast as we need it to change. So let's just look at a typical electricity that most of us use comes from burning coal. So we have potential energy in coal. We'll explain why it's there in a different session. But basically, there's chemical potential energy here. I react with oxygen, and the chemical potential energy in the coal is converted to heat energy. And the problem with heat energy is it's energy in the random motion of atoms. And random motion is there's not much. I don't want randomness unless I'm trying to heat myself up. I want things to move. I want to be able to do something with this energy. And so fortunately, very clever people figured out, I know what we can do. If I boil water, I make steam, and I can make steam go in the direction I want. So in steam, it's just randomly moving water molecules in a vapor state. But by opening up an outlet to them, I force them to go all in one direction. So it's a way of converting random energy of motion, heat energy, thermal energy, into kinetic energy, just directed motion. So basically, we pump water in. It goes to these pipes. Heat energy is transferred from the coal to the pipes, turns it into steam. That steam turns this turbine, and that in turn turns this axle, which turns the coils of wires inside the magnetic field, which generates the movement of electrons in the wires, which we send out to a nationwide grid, and everyone gets their electricity. We distribute around the country. Now, I have to have a pressure difference. So it has to come in as high pressure steam and go out as low pressure, which means I have to have a way of condensing it back into a vapor. So what I do is I have to pump water in here, and basically the job of this water is to cool the steam back into a liquid state so that there's a reason for the steam to move from here to here. If we didn't do this, it'd be pushed just as much this way as this way, and this wouldn't spin. So these condensers are necessary, but unfortunately, it ends up wasting a lot of energy. Now, what happens then is this water that we use to condense this ends up picking up some of the heat. We let some of it go to the sky, and then we had to pump some of it into the river. And unfortunately, in doing so, we introduced some thermal pollution to rivers, which we talked about earlier. Now, let's look at a nuclear power plant. It's almost the exact same thing. All right. Look, I'm just going to look at where it's the same. Okay, look at this. I still have pressurized steam turning a turbine, which turns coils of wires inside a magnet, which causes electrons to be energized in the nationwide grid. I take this water, I have to condense it back down to a vapor state so that there's a reason for it to flow from here to here, high pressure to low pressure. That means I have to condense the water, I have to send it up here to cool it off and release it to a river. Everything on that end of it is identical to coal. The difference is on the other side here. In here, instead of burning coal to release chemical potential energy, I'm setting up a nuclear chain reaction in uranium-235 atoms, again, which we'll talk about, to release heat. And then I still think I have to take this heat and I have to somehow use it to make steam. So in this case, I pump water or another liquid, like say liquid sodium, through this system, through the reactor core, where it's going to pick up some radiation. So, and then I make it go through some pipes where it's going to transfer its heat energy to water, causing the water to boil. And so, but you notice it's pretty much the same thing, except with a little bit of difference here, since I'm releasing nuclear potential instead of chemical potential energy. All right, now, the thing is, though, this is a very inefficient system. So let's just talk about what efficiency is. Efficiency is simply the percentage of the energy that I converted that ended up in the form that I wanted. So what percent of the energy that I transformed ended up as the kind I wanted? So if there was no second law of thermodynamics, then ideally we would want to take 100% of the energy present in coal, say 100 joules of chemical potential energy in coal, and turn it into 100 joules of electrical energy. So 100 joules chemical to 100 joules of electrical, that would be 100% efficiency, right? But that's not what we get, and that's not possible. Second law of thermodynamics says no matter what, some of it's going to end up as heat. Unfortunately, a lot of it ends up as heat. Let's go back and look at this. I burn the coal. Now look, you know what? The sides of this plant are getting hot. The pipes here are also getting hot. The steam comes out here. It makes this hot, all right? There's friction, which makes these parts hot. then I have to like turn this back into liquid water. So a lot of the heat energy just ends up going up here as evaporation or into the river. Most of the energy does not end up going into the power lines. It is appalling, but I hate to tell you this, a third of it ends up in the power lines. Two-thirds of it ends up wasted as heat energy. So we would say that the efficiency of a coal-fired power plant is 33%. That means 33% of the joules that come in as coal go out as electricity. The other 67% just end up as wasted heat energy. Okay, so it's not that we destroyed energy, it just got converted to heat, which we didn't know what to do with, because it's hard to do anything with heat unless you can make steam. Now, unfortunately, energy is also lost in power lines. Okay, so basically, without getting too much into it, there is what we call electrical resistance. Think of it like friction. So when an electron moves through a wire, it encounters this resistance or friction, and that means just when friction in my hands converts to heat, this resistance or friction in the power line converts it. So every electron that moves in that wire is going to encounter that, and the greater the distance of the wire, the more of that energy it's going to lose. That's one of the reasons we try to position power plants as close to cities as we can to reduce the length of those wires, to reduce the amount of energy that's lost being transmitted from the source of the generation to your home. But the problem is we're using coal, and coal produces air pollution. So we don't want to move it too close to the city, because then we end up with all these health problems. So there's this balance about how far away from town can I put my coal. I'd love to put it far, far, far away, but then I gotta lose a lot of electricity. But they came with a very clever idea about 100 years ago. They said, hey, yeah, basically, without getting too into it, voltage is a measure of how much energy an electron has. And so instead of, like in our homes here in Korea, we use 220 volts. Well, that means I'd had to send a whole bunch of electrons to your house that way, and every one of them would lose energy through resistance, through the friction of resistance passing these wires. So they come with this great idea. We're going to transform it into very high energy electrons. So instead of having, say, 200 low energy electrons, I'm going to turn it to 200. I'm going to make each one of them 1,000 times more energy, and that means I can transmit 1,000 times less electrons. So basically, I'm sending a few very high energy electrons through the wires instead of a whole bunch of low energy ones. And then I'm going to convert them through transform them back into a bunch of low energy electrons on the other side. So the bottom line is we use high voltage power lines in order to improve the efficiency with which we transmit energy from where we liberate it out of the coal to where it gets into your home. Now, the reality is the power lines are pretty good. They have about between 90 and 98 efficiency, depending on how long they are. So that's not so bad, but still, it's another place that we end up losing electricity. Now, when we talk about the companies that manufacture the energy for us, that liberate this energy from coal for us, we tend to call it the power company. So let's talk about what power is. Power is a measure of the rate at which energy is converted from one form to another. So rate means you have to divide by seconds, right? So we measure power in a unit called watts. I'm sure you've heard of watts. Watts just means the rate at which energy is converted. So the rate at which coal is converted to electricity, the rate at which electricity is converted to light. It could be the rate at which gasoline in your car is converted to the motion of your car. Any energy conversion is measured in watts. Okay. Now, 1 watt means that we're converting 1 joule of energy every second. So 1 watt equals 1 joule of energy converted per second. So therefore, a 24-watt light bulb converts 24 joules of electricity to other forms, preferably light, but second law of thermodynamics, some of it to heat, every second. 24 joules of energy is going to get converted from one form to another every second. We call it 24 watts. Now, because people consume energy at a certain rate or wattage, we tend to rate power plants in terms of the wattage that they can produce. And so a kilowatt would be 1,000 watts. And that's kind of a rate at which your home is using it. Your home tends to use energy in the kilowatt range. Power plants tend to produce it in the megawatt range. Okay, so that would be 1,000,000 watts, or 1,000,000 joules per second would be 1 megawatt. And larger power plants are producing gigawatts. That would be 1,000,000,000 watts, or 1,000,000,000 joules of energy being converted every second. So a typical coal-fired power plant is generating about 500 megawatts, or 500 million joules per second. And a typical nuclear power plant is producing about a gigawatt, that means 1 billion joules of energy is being converted every second. Now, when you get your electrical bill, you'll notice that it's worth noting that what you pay for is energy, which is measured in joules. You don't pay for the rate at which you use it. You don't pay for watts. They don't care how fast you're using energy. They just care how much of our coal did you use? How much energy is your responsibility? All right, and so, but the thing is, you typically use like thousands of watts, right? That means that you're converting thousands of joules per second in your house. So people don't like these huge numbers. People don't like scientific notation, right? So, well, I do, but your typical person doesn't. So when they try to report to you how fast you're using it, what they tend to use is a term called kilowatt hours. So a kilowatt hour, which is K capital W H. So 1 kilowatt hour means the amount of energy you converted in 1 hour. So a kilowatt is 1,000 watts or 1,000 joules for 1 hour. So if I convert 1,000 joules a second for 1 hour, how much energy do I produce? Well, that's 1 kilowatt is 1,000 joules per second, and there's 3,600 seconds in an hour, 60 times 60. So that means that 1 kilowatt hour is 3,600,000 joules. And so a typical U.S. home, their electrical bills say about 900 kilowatt hours, or 900 times this. So that's a lot of joules. So you can see why people rather see the number 900 than 900 times 3.6 million. All right. That's it. Thanks for listening.